Hi, I am Sung Min-jo, Director General of the Center for Smart Construction Technology of Korea Expressway Corporation, and in charge of the Smart Construction Technology Development Program. Digital transformation wave based on cyber-physical systems, Internet of Things, drones, big data, artificial intelligence, virtual reality, and blockchains are interconnected for convergence, has established as a key for innovation in all industries. Governments and construction companies also recognize digital technology as an essential tool for survival. Innovative companies and startups have focused on commercialization for smart construction with various innovative technologies as the basic tools. Today, I am very pleased to give a keynote speech on smart constructions for the 17th East Asia Pacific Conference on Structural Engineering and Construction. I will talk about digital-based technologies for smart constructions. This is also an introduction of Korea's national research program to develop smart construction technology. I will present technology trends shaping the smart construction and its industrial application in Korea, focusing on the road sector. Before presenting the topic, I would like to introduce my organization. Korea Expressway Corporation, KEC, is an authority for the National Expressway System of Korea under the Ministry of Land, Infrastructure, and Transport of the Korean government. And the Center for Smart Construction Technology is the managing body of the National Research Program to develop smart construction technologies. It is responsible for implementing the research projects, demonstrating developed technologies, and promoting smart construction in the industry. Construction is the world's largest industry, but productivity and profitability are low and the most current processes are far from digital. It has become a digital era. Digital influences the fate of an industry. Paradoxically, the pandemic caused by COVID-19 has been the catalyst for digitalization. Now, digital is leading industrial innovation, and more people are interested in digital transformation. As a new normal, digitalization is rapidly changing the global construction market. The size of the smart construction market in 2025 is estimated to be up to $1,570 billion. The governments of major advanced countries are implementing various policies for the digitalization of construction. This shows a brief timeline of smart construction policy of Korea. In 2017, Korean government reflected the vision of smart construction in the National Comprehensive Plan for Construction Technology Promotion and established the Smart Construction Technology Roadmap in the next year. In particular, Korea started a large-scale national research program according to this roadmap. Since last year, KEC has mandated three-dimensional BIM design instead of two-dimensional design. Smart construction is defined as a construction method or system of achieving automation of the constructing process, data-driven operation, and virtual construction by converging digital technologies to secure high productivity and safety from the construction stage to the operation and maintenance period. Simply, it is a digital transformation of construction. Then, how will the smart construction change construction work? First, the 2D drawing-based design is changed to a 3D digital modeling called Building Information Modeling, BIM. The current 2D design is changing to 3D design based on Building Information Modeling, BIM. By using the property information contained in the 3D model, 4D to manage the construction schedule, 5D to manage the quantity and the cost, and finally, EASEC17 management for life cycle maintenance becomes possible. I will introduce an example case of an application of BIM for interchange renovation works for road construction. The survey was conducted using a drone for the project area. For BIM design, first, the alignment and the geometry of the road were determined and assigned to the route. Next, the bridge was modeled. This model was again assigned to road routes. Then the earthwork section was modeled. The BIM result looks like this. We can visually check the location and the shape of the newly created ramp around the current expressway route. After the modeling has been completed, we can see the cars passing on the expressway in advance. In addition to daytime, it is possible to check the condition of the expressway by considering the lighting for each time zone at night. Finally, it is the status of the work progressing according to the construction schedule, that is, a scene in which 4D management is performed. Survey and data collection technologies based on UAV, UGV, camera, LiDAR are evolving and improving rapidly. Instead of humans, drones and robots will create 3D digital maps and collect various information on construction sites. However, the abundance of solutions and systems available today can make it difficult to identify the best option for construction and civil projects. It needs to examine each system's benefits and limitations in construction management and civil engineering. The use of mechanized construction equipment at construction sites is common. Furthermore, unmanned or remote control technologies using automated equipment are being used. We generally divide machine automation into MG, machine guidance, and MC, machine control. A trend in the industry is for guidance systems to become increasingly automated. The equipment used for earthworks is remotely controlled and autonomously operated. Graders and rollers can be operated autonomously through hydraulic system control and automatically along a set route. Equipment put into the field is managed according to the integrated control system, and the communicates with each other through pairing between equipment. SiteCloud, provided by a company that produces construction equipment, introduces digital automation technology. A digital construction platform supports management based on 3D visualization by integrating drone data, underground data, and design data. Fleet location tracking and operation monitoring in real time. SiteAuto is a construction automation system. 3D machine control combines 3D machine guidance with automatic hydraulic control system and can be applied with a tilt rotator attachment. Site safety is a construction automation system enables safety management by location tracking of construction equipment and workers with IoT technology. 3 The sequential construction phase is changed to a system in which design and construction are interconnected based on a digital model. In addition, off-site construction, which means prefab and modular construction, is generally applied. At Kodak Bridge, which will be the world's longest concrete cable-stayed bridge, mobile monitoring of hydration, heat, and proximity warning around equipment are also being used. The temperature during concrete placement was automatically recorded and managed using the temperature sensor and IoT communication installed in the rebar of the concrete structure. Based on the BIM model, virtual reality was used to check whether the members of the bridge that had been constructed were made according to the design. And the tower crane for the construction of a high located pylon was equipped with a sensor and communication-based proximity warning system and operated safely. A common data environment for collaboration based on BIM is also being operated for the first road tunnel construction under the Han River in Seoul, and integrated construction management using a platform consisting of a smart dashboard, digital twin simulation, and IoT system is also being used. Web-based 4D simulation using BIM workers' location tracking are also tried. Digital technology can be greatly contribute to the improvement of safety in the construction industry, which is classified as the most dangerous industry due to many accidents during work. Various sensors, Internet of Things, and communication technologies will help increase the safety of construction sites. Virtual reality technology based on 3D digital model is very helpful in preventing accidents by educating workers before work. Off-site construction cases using prefabrication and modular technology are also increasing. It is also used in piece segments of tunnel boring machine, tunnels, culverts, etc. This OSC technology is also widely used in bridges. Incheon Bridge, Korea's longest cable-stayed bridge, and Turkey's Çanakkale Bridge, the world's longest suspension bridge, completed last spring, are results of the accumulated prefabrication technology of Korean construction companies. In 2020, the Korean government started a large-scale research program to develop smart construction technology by 2025. This program consists of a total of 12 projects in 4 areas. Areas are earthworks automation and site data collection, prefabrication, design for manufacture and assembly, and structure automation, smart construction safety, and data digital delivery platform and test beds. The ultimate goal is to use digital technology to increase productivity and digitalization in the construction industry, and to lower the construction period and accident rate. The Center for Smart Construction Technology of KEC is leading the program, which has been funded by the Ministry of Land, Infrastructure, and Transport. 131 organizations take part in this program. As mentioned above, the research program consists of 12 projects in 4 areas, 3 projects in each area. The first group researches intelligent control of construction equipment, collection and analysis of site information, and digitalized automation of construction equipment. The second group researches BIM-based support of design, fabrication, construction for prefabrication, remote controlled and automated construction for bridges and tunnels, and quality control for prefab during transport. The third group covers integrated system for smart safety control, securing safety for construction workers and safety measures for temporary structures. The fourth group will play a role in standardizing the data, creating a platform, and demonstrating each technology by covering the previous three areas. The group researches data integration, smart delivery, and knowledge-based management, digital platform and virtual construction using digital twin. Finally, testbed operation. I will briefly explain the contents of the developing technology, focusing on each area using videos. Earthworks automation and site data collection. This is to develop technologies by integrating the site information acquired through autonomous measurement using drones, unmanned ground vehicles, and various sensors to create a digital map, and combine it with equipment automation for road construction. Target technologies are intelligent equipment control, unmanned navigation of construction fleet, autonomous building of digital map, digital twins-based site information collection, autonomous operation of equipment, and advanced quality control for earthworks and paving.
To digitize the topographical information of construction sites, we are developing AI-based drones and ground-moving platform UGVs that can operate autonomously. By integrating the on-site topographic information acquired through the drone autonomous measurement system and UGV, it creates an ultra-precise 3D digital map required for construction works, such as earthworks and pavement works. The manager can view the site's topographic information that changes every moment in the control center. It is a mobile control center equipped with an intelligent construction equipment control platform. By reflecting real-time field information based on AI, it can autonomously judge and respond to the operation of construction equipment at various levels of automation such as MG, MC, and unmanned remote. Intelligent control technology is the interaction between equipment and the control center, or between equipment and equipment. The productivity of earthworks and pavers' work is dramatically improved. Through communication between different types of equipment, such as dumps and dozers, it is quickly determined which equipment to pair with when two construction equipment approaches within a set range or arrives at a designated location. We develop intelligent construction equipment capable of autonomous work, driving, and remote control. Utilizes high-precision electro-hydraulic control technology to realize the automation of the operation of rollers, graders, and dozers. It monitors construction quality and work volume in real time through sensors linked to the equipment. The equipment follows the planned route by itself and runs, and it is possible to avoid unexpected obstacles. By utilizing the pendant remote control interface, remote control can be performed quickly on site in case of emergency, and remote control is possible even from a distance from the control center.
Prefabrication according to design for manufacture and assembly, and structure automation. Development of technology that employs BIM, artificial intelligence, 3D scanning, prefabrication, and robotics to improve the design, fabrication, construction process and support collaboration between each process to build bridges and tunnels. And development of a remote control and automation technology for structure construction to address the factors that impede productivity due to dangerous and poor work environment. Target technologies are digital engineering modeling of prefabricated bridges, manufacture and assembly of prefab members of bridge, automated construction of piers and girders for bridge, artificial intelligence-based operation of tunnel boring machine, configuration control of prefab bridge construction, and structural integrity monitoring of prefab members during transport. We will design and build prefab members using 3D digital engineering models. Remote-controlled multi-crane equipment installs the bridge girder, and the drone tracks the construction status. IoT sensors monitor the quality status of prefab members manufactured in factories during transport, and use robots to construct piers in high places automatically.
The second field of smart construction development project is develop prefab structure design, manufacturing, and construction support technology based on data-driven engineering. Digital engineering model is a technology to design an automatic connection with road alignment. By simply inputting data, the structure reflecting the road alignment is automatically designed and a BIM model is created. DEFMA is an abbreviation of Design for Manufacture and Assembly, and is a design technology that interlocks prefab member manufacturing information. Using this technology, prefab members are automatically produced through the process of rebar assembly, casting, curing, and face treatment by robots. It was developed so that the quality test is automatically performed through scanning the member. The prefab method necessarily includes transportation procedures. Even if the manufacturing quality is secured, prefab members can be damaged during transportation. Quality track technology is being developed using smart sensors during transportation in order to minimize on-site manpower. A construction technology is being developed that remotely controls the robot from the control center. From the existing method using slip form, a construction technology is to develop that automatically raises the formwork and connects the rebar using special robot. Can be performed remotely and precisely. We try to minimize on-site manpower in construction and prevent equipment collision accidents. A multi-crane collaboration system is being developed to minimize on-site manpower in construction and prevent equipment collision accidents. In the whole process, the assembly process of girder slab is the most difficult. To assist with this, we are developing a technology to determine constructability by pre-comparing site and member scanning information. Like this, developing data-driven smart construction technology is going on.
Smart construction safety. development of smart safety integrated control system using cloud, big data, artificial intelligence, Internet of Things, sensor network, and edge computing. System capable of detecting, assessing, and predicting risk factors that may occur during the installation, dismantling, and operation of temporary structures that are relatively disregarded in management. These areas' target technologies are data mining-based safety analysis, emergency response technology, safety control system based on digital twins, automatic detection of hazard factors of workers, risk assessment, and quality verification of facility and material for temporary use.
Worker wearing smart safety device. Let's go to the test bed site. You can check various risk factors in the field based on location and image and take action in advance. Various sensors enable real-time on-site change measurement, worker abnormal behavior, and non-compliance detection. Temporary equipment damage and crack information can be detected. A robot dog equipped with LiDAR can remotely check the 3D shape information of temporary structures and determine whether there is an abnormality. A drone equipped with a camera can perform inspections on vulnerable parts of temporary structures. Construction sites are controlled in real time through video, and dangerous situations such as emergency disasters, such as fires and earthen barrier collapse, and worker collisions can be monitored and responded to based on the safety control VM. Safety-related data for individual sites is managed by the Integrated Safety Control Center, and this data is provided to the government, local governments, and the Korea Expressway Corporation General Operations Center.
Data, digital delivery, platform, and test beds. This is to develop the technology for provision of information and services appropriate for digital platform users by integrating data acquired in the construction process regarding the standard, and with analysis and compilation of the data, and operation of comprehensive test beds to verify the developed technologies. Fourth area's target technologies are integration and standardization of digital data, knowledge management system, digital delivery system for prefabrication, real-time data collection, building of digital platform, construction simulations and visualization of construction process using digital twins and artificial intelligence, operation of comprehensive test beds, and policy development.
This is the test bed site where the development technology will be demonstrated. We will enter the General Operations Center that controls and operates the information on the test bed site. Topographical and earthwork automation data in the first focus areas is collected from the on-site edge system, and the information processed on the platform can be checked at the General Operations Center. Prefab structures in the second focus areas also provide information from design to manufacturing, construction, and quality control. You can check it through the platform. Construction sites safety information in the third focus areas can also be controlled by the General Operations Center, and the related information is delivered to the relevant organizations to respond quickly. As such, all data from the test bed site is collected through a digital platform and processed into information that can be exchanged and utilized through data standardization. By applying image processing and machine learning technology to various structured and unstructured data such as BIM and IoT, sensor data accumulated in the data lake of the platform, digital twin-based decision-making can be made. In the office, you can simulate the construction process in advance in a virtual environment through VR. In the field, you can immediately check the necessary information during construction through AR. A chatbot that can recognize both voice and text transforms fragmented data into knowledgeable information. In this way, digital transformation of construction sites is realized by collecting, utilizing, and sharing all data through the cloud-based platform.
The driving forces of smart construction are the enormous increase of data, new technologies, distinct benefits from practices, the government's strong drive, and desperate hope for carbon neutrality. Since 2020, the Korean government rewards excellent cases through the Smart Construction Challenge competition every year. KEC also encourages smart construction by discovering and rewarding best practices in national expressway construction projects. These are award winners of a Smart Construction Challenge in 2021. As I wrap up the lecture, I'd like to share some thoughts to open a new horizon of smart construction. Who is the leader of digital transformation in the construction sector? BIM is just an essential tool. Data is the key. Digital transformation is an entirely new one. So, we need to find a new value for smart construction. Thank you.